Good evening, everyone, and welcome to the July and a half meeting of the RASC Ottawa Centre. I'm Mick Wilson. I'm your congenial host for the evening. Looking forward to have a very exciting presentation, but with all the business from James Webb this week. And so with that, Chris, please move us along. Usual heads up, we are recording this webinar for posterity. It will be available at ottawa.rasc.ca. If you have questions for the speakers, please use the Q&A. Chat box comments can be seen by all but aren't monitored for responses, and raise your hand is disabled. Next, please. Okay, so tonight's program, hello, I thought that was updated there, Chris. So yeah, hi, again, I'm Mick Wilson. I'm doing this introduction. There won't be an update from the RASC GA. We'll put that off to the next meeting. Following this, Chris Chisholm will be doing the regular Ottawa Skies for this month. Then we have our first special guest speaker, welcoming back Jesse Rogerson, to give us the lowdown on the actual sort of science data that's come out of the James Webb Space Telescope this week. And that'll be followed by Simon Hanmer doing what? His 60-second presentation, I think, Chris, this time on inner solar system science over the last year and a half. The normal break, AstroTrivia, followed by Rick Wagner, giving us an update on one of the RASC's certification programs, in this case, Astro-imaging. Then we'll have our observation reports and various closing out announcements and the observing challenges. So with that, Chris, I think it's over to Dave. My mistake. New members. 2 new members this month. Welcome, Lee. Welcome, Claude. Hoping that you're on the call and hoping that I can harass you to become, in the near future, new presenters to the RASC Ottawa Centre. 30 members so far in 2022. Meanwhile, 2 members in the news. First of all, Chuck O'Dale with his article, Chris, next one. In the last edition of Sky News, his article on his lifelong passion of searching out astroblems, craters, and exploring them through his own flights and exploration around the country. So, well done, Chuck. Good for you. Andrea Gironde has had her photo picked as the photo of the week of the Zodiacal Light, which he submitted. And if we can go to the full screen for that one, Chris, the next shot. An absolutely beautiful shot of a hard to spot phenomenon, Zodiacal Light, and well done, Andrea. Next one, please. Meanwhile, we have the ongoing Sky News Reader's Choice Award voting, and we have 2 of our Ottawa members as participants in that. Next slide, please. So we've got both Pierre Martin and, again, Andrea. I personally find it incredibly difficult to vote, not only for any of the shots from our members, but for particular shots that are brought up into this contest. They are all so stunningly well done, beautiful, superbly executed. So Everyone's
the contest is
excited
actually
to
closed,
go.
Mick, now. The contest closed.
Okay.
Yeah, it closed a few days ago. If we were having the meeting last week, we could have voted.
It would have helped boost the votes. Okay.
Yes.
Thanks, Dave. So, next slide, please. We still have an outstanding offer from Calvin Klatt to host, or at least guide, external tours of the original Dominion Observatory. He originally proposed this back in June. We're sort of running out of July now, but still, I think Calvin's offer is still open. Learn the history of the Dominion Observatory, maybe have a social event, a Barbie, something like that associated with it. So far, not so many expressions of interest, but as I say, the offer is still open. And please forward them to me as meeting chair at ottawa.rasc.ca. Next, please, Chris. Membership. Why be a member of our society? We'll go through a bunch of the benefits in a few seconds. Just if you can back up one there, please, Chris. There has been an increase in fees since last month's meeting. This is as a result of increased cost for member services and in particular printing, distribution of the materials that are provided to everyone as part of their memberships. The cost, $103 for a regular, $97.50 plus some individual costs for each family member, and a $62 and can't see that. Yeah, $62.40 for students and under 21-year-olds. So what's the point of joining? Next one, Chris. Under normal circumstances and in the near future, you have access to physical resources, in particular the Ted Bean Loan Library and the physical book library, both of which are at the Canadian Astrospatial Centre. In the meantime, until the centre reopens, there is the members' access to the Fred Lossing Observatory just outside Ottawa, and participation in the members' certificate programs, about which we'll hear more from Rick Wagner later in the meeting. Next one, please. Meanwhile, there are the publications, both online and on paper, if you subscribe for them. Sky News, the bi-monthly newsletter for RASC, the academic RASC Journal with scientific and historical papers, the Observer's Handbook, which will obviously soon be presenting its 2023 edition, and our own fabulously successful Astronauts, the local newsletter for the RASC Ottawa Centre. All yours for joining the RASC. Next one, please. My favourite pitch is the community, the people that you will interact with, be able to gain knowledge and experience from. That's both our presenters and the local members. An absolute steal for the cost of membership in RASC Ottawa or the RASC in general. So please join up. Next one, Chris.
Okay.
And now, over to Dave.
So let's see what's happening for the skies in July. We're already halfway through, but that's okay. Let's nothing too important we have missed, except we missed the full moon, supermoon on the 13th of July. Hopefully some of you folks saw that. And that moon was called the Buck Moon. and it's also been known as the Thunder Moon and the Hay Moon. It's the second of 3 supermoons in 2022, and the moon will be near its closest approach to Earth. It may look slightly larger and brighter than usual, but I've never really noticed a difference with a supermoon. Next slide, please. We have the Delta Aquarids meteor showers, July 28th and 29th, and it's about 20 meteors per hour at its peak, and it will peak either side of July 12th to August 23rd. You'll be able to see them, but it peaks on the night of the 28th and 29th. Appears to be radiating from Aquarius, best viewed after midnight. Sun, you can see the days are starting to get a little bit longer as we move through the month. Or sorry, getting a little bit shorter. That's what I should have said in terms of sunlight. Mercury's not visible. It's rising and setting with the sun. Venus is visible in the early morning. Mars is visible in the early morning, but as you can see, as we move towards the later part of the month, just after midnight, we'll be able to see Mars. And next month, we'll be able to see Mars in the evening sky. Jupiter, visible late evening and through the night. By the end of the month, we'll be able to, it'll be rising at 10:49. So realistically, we probably will see it about 11:30. So we'll start to see Jupiter in the evening sky. And Saturn's even earlier. By the end of the month, it'll be at the horizon at 9:10. So probably 9:45 thereabouts, we'll be able to see Saturn in the evening sky. Uranus is visible before sunrise, and Neptune is visible late evening and through the night. And here is our cartoon of the month. I Googled Curiosity Killed the Cat, and I was not disappointed. And Chris, I think we have some breaking news. Oh, yes. This is a crater from a hard meteor impact in Arizona. Oh, and this is in Australia. That was for you, Mick. Thought you'd enjoy that. Okay, folks. I'll turn it back to you.
Thank you, Dave, as always. Okay, we can move along now. Thanks, Chris. So I'd like to introduce our guest speaker for tonight, Jesse Rogerson, an old hand at RASC Ottawa presentations. Used to be at the Aerospace Museum, a regular presenter, I think half a dozen times over 4 or 5 years there. He's since moved on to York University, but has graciously consented to come back and give us the scientific update on the images from JWST, released earlier this week. With our meeting delayed from last Friday, this is actually a really good opportunity for us. So over to you, Jesse. Thanks.
Okay, thank you. Hello, it's good to be back, everybody. I really miss Ottawa, and I miss the Ottawa RASC crew, and I miss when you would go and do your meetings in the theater, in the auditorium on those Friday nights. Yeah, nothing can replace the time that I had at the museum and the time I had in Ottawa. So I'm happy to be in Toronto in my current role, but I definitely missed my previous role. One thing, okay, so we're going to talk about JWST images. One thing I just want to put out there right away is I'm not a JWST scientist. So none of the data is mine, and I don't have any proposals into JWST at the moment. So I am coming at this as an enthusiast, very much like all of you watching. So I first got to see the data when they released it on Tuesday with the rest of the world. So if you watched the data drop on Tuesday, then there's much more information there than what I can handle today. This is only going to be a short presentation, just giving you a couple of images and a couple of images that came out today over the last 24 hours. So this is more just to whet your palate to get interested in the JWST stuff and go doing some more digging. So let me share my screen here. Oh, there's a Q&A. Oh, what is JWST? Thank you. Thank you for that question. And I love the Q&A thing set up. JWST is the James Webb Space Telescope. And it, sorry, let me just, 1 second, share my screen here. Share screen. There we go. Okay, so you should all now be able to see my screen.
And Jesse, it's just Chris interrupting for a second. While you're presenting, we'll monitor the Q&A for you, so you don't have to be multitasking too far, and we'll pass the questions on to you. If you happen to see them, great, but you don't need to multitask.
Okay, great. That's good to know. Okay, thank you.
So Jesse, you may want to maximize there. We can see your screen background.
Yes, I did this on purpose just for a second because I put it in the chat box, and I don't know if anybody's watching the chat box, but there was the mention of the Dominion Observatory earlier in this by Mick, I think maybe, and the Ingenium, which is there's the Aviation Museum, there's the Agriculture and Food, and there's the Science and Tech logos there. Ingenium has this blog, 4 blogs, 4 posts about the Dominion Observatory. So if you really want to dig into the history of the Dominion Observatory before you go see it, read these 4 posts. They're fantastic, very in-depth in their history, and you learn a lot about Ottawa and learn a lot about the history of astronomy in Canada. So give it a shot. And here is for, I unfortunately was not prepared with an image of JWST. So I want to find one for you. So you can see, there we go, what JWST looks like. So this is the James Webb Space Telescope. Where's my maximize? This is a computer animation of what the James Webb Space Telescope is, JWST. It is an infrared space telescope that was launched into space back in December. Had to fly out to the Earth's L2 Lagrange point, which is a point millions of kilometers away from the Earth. And its job is to look at the universe in the infrared. It has a 6.5 meter collecting area with these gold-plated mirrors specifically designed to look in the infrared. And it has this giant sun shield designed to block the sun and block sources of heat from hitting any of the instrumentation or the telescope, so they can cool this thing way down, make it nice and cold to do its infrared observations. It is literally about 25 years in the making for this thing. So the launch of JWST in December and then the subsequent data release on Tuesday was a big deal. It was careers for people, and with the notable heightened intensity or heightened stress that everybody was really worried that it wasn't going to work because it was such a complicated machine. It is such a complicated machine. All the engineering, we don't have time to go into it. But if it did break, then there's no way to fix it in the way that Hubble could be serviced. There's 4 or 5 Hubble servicing missions that went on from 1990 something to 2008, 2009. I can't remember when the last one was. And so Hubble was visited frequently because it's only like 600 or 700 kilometers away, whereas JWST is inaccessible. So it had to work perfectly. And Tuesday showed us that it did work perfectly. So let me, how do I get this down? There we go. And let's go through. They released 5 images. As you all know, okay, so I'm going to try and keep this brief because I could literally go on for hours about this. In the way that the Hubble Space Telescope does the Hubble Deep Field images, these are iconic images. There's the Hubble Deep Field, the Ultra Deep Field, the Extreme Ultra Deep Field. Basically, you take the telescope, you point it in a direction, and you expose for hours, in the Hubble's case, for weeks to create those images, collecting photons. Here's the very first image they released. It's the Webb's first deep field. It's 12.5 hours of exposing time on a galaxy cluster called SMACS 0723, MAC 0723 right there. I'm going to say just a couple of things because I just don't have time to go into detail on all of these. This is a galaxy cluster. So we're talking about a few thousand galaxies gravitationally bound to each other. In this image, those galaxies are like the bluish things, the blue and white images things. The only things that are not part of the cluster, well, there's two parts. These spiky things, those are foreground stars. So there's one there, one there. Those are stars in our galaxy. Then the blue and white-ish other things like this one here, all these ones here, that one there, that's all part of the galaxy cluster. And then the red images, the red things you see, most of them are background to the galaxy cluster. They are actually a range of distances away from us. And some of them are some of the earliest galaxies that ever existed, going back 13.1, 13.2 billion light years away. So the cluster itself is at about 4.5 billion light years. And the cluster is lensing, magnifying galaxies beyond, galaxies that are really far away, way back at the edge of the universe. And what I want you to think about here is, this is kind of what happens here is they took JWST and pointed it at a magnifying glass, meaning like to amplify its ability to look far away. And here's the same. So there's the James Webb image, and some of you may have seen this go make the rounds on the internet. And there's the same image or the same place on the sky as Hubble. So you can see already, but there's a little bit of apples and oranges here because Webb is an infrared, Hubble is an optical UV telescope. So it's a little bit of apples and oranges, but one thing you should take away is that the resolution is better, and because its collecting area is much larger, it can achieve depth quicker. So it can get a deeper image into space much, much faster than Hubble could. Okay, I need to keep moving because otherwise we're not going to finish. Just in case you're wondering what kind of science we can do here, if you're a spectra person, if you really like to get into taking the light from a galaxy and breaking it up into a rainbow with like a prism or something like that, here's what they did for a few of them. So you pick like this galaxy, this little red galaxy right here, this little tiny point of light. And if you, there's it zoomed in right there. And if you break it up at that light, all of the light in this image right here into a rainbow, you'll see peaks of light indicating hydrogen, oxygen, and hydrogen right there. So this is telling you stuff about the galaxy. But the important thing to note is those same 3-4 emission features can be found in most galaxies. However, the further away a galaxy is, the further it's shifted to the red. So you can see this one's 12.6 billion light years away. This one's 13.0 billion light years away. There's 13.1. And you can see the structure, the hydrogen, oxygen, hydrogen lines are shifted into the red, indicating they're further away. So they can do some science with this. I'm sorry for the speed that I'm going on here. I just wanted to sort of impress upon you that there is science being done. And that one that's 13.1 billion light years away, that little red dot, they can really dig into with the resolution that JWST has and really pull out some really interesting features. Like, look at these were the lines I was showing you before, but you can see some neon here and some more oxygen and hydrogen. So they're just able to, at first glance, look at the light coming from these galaxies and see what they're made of. And Gerald asks, sorry, Chris, I'm going to just say, Gerald asks, how do we get colors in infrared? Great question. Color is just a term that we think of colors with the colors that the human eye can sense. But all color is just us experiencing different wavelengths in different ways. Like red is a different wavelength than blue, is a different wavelength than green. And in the infrared, there are certain kinds of, there are short wavelength, longer wavelength, bigger wavelength, and so on. So while we can't experience it with our eyes, we call them colors in astronomy because it's basically the same thing. A common thing we use for color in astronomy is just subtracting two filters. So if you take an image of the sky in one filter and then an image of the sky in another filter and you subtract them, then that's a color image. It's just a catch-all term for a specific wavelength. So on this telescope, they have a few different filters to filter out specific wavelengths. What is the detector gap? Chuck, oh my gosh, good question. That is literally the cameras. This are made, like the sensors are made of CCDs, and you put two CCDs up against each other. If you make a big CCD, what you end up doing is you actually end up making little CCDs, and you patch them all together, and then they end up having gaps in between them. So what we do in astronomy, this is in most research telescopes, any sensors really. What we do in astronomy is we'll take an image of something or a spectrum of something, and it'll have the chip gap in it that you see. There's the detector gap. But then what you do is you just move the telescope a little and then take the image again. And then you fill this in with another image is what we end up doing. You're actually not moving the telescope, you're moving the grating. It's a lot of detail, but yeah, that basically it's portions of the spectrum that couldn't sense anything because it fell on a place where there were no sensors. And here's what time am I at? Oh my gosh. I'm still on the first image of 5, right?
Don't panic, Jesse. Take your time.
This is the same one. And one thing I didn't point out, which I will point out now, is all the streaky stuff. Those and it almost looks like a bullseye or like a circular pattern that you see. Like there's circular ones there and there and there. That's all effects of the lensing. It's imagine it's literally like a big magnifying glass. The foreground galaxy cluster is magnifying the background stuff. And the way it does it is by bending light around it, by curving space-time. What they were able to show with one of Canada's instruments is these two right here, that image and that image. Okay, can you all see that still? Okay, from that, they took a spectrum of this one and a spectrum of this one. And there you see the two spectra right there. And then there's the graph version of those spectra showing that they are indeed the same galaxy. Two images of the same galaxy created by the lensing effect. It's wild. Lensing is one of the coolest things that happens in the universe. Just comes out of the fact that mass bends space-time. A galaxy cluster creates a bend and light follows it. And so you can create lenses. You can create magnifying glasses. It's wild. Okay. That was the first image. That's just the tip of the iceberg of what you can do with a deep field image. We didn't even talk about galaxy evolution. We didn't talk about stellar evolution or the initial mass function of how stars are born and how many stars we have of each star. So we can go on. This was the second or third image. I don't know if I'm putting these out in the same order that they did. This is a spectrum. So it's not an image of the sky. It's a spectrum of the sky, a spectrum of a specific star. So this is starlight that has been filtered through an atmosphere of a planet orbiting that star. So what do I mean by this? Here is the star. This is a computer animated version. Here's the star. It's called WASP 96. And then around that star is a planet called WASP 96b. So there's the planet, and it goes around and around, just like planets go around stars. A couple of differences with this one. This is a planet that has an orbit around its star that is 3.5 days. So think about that for a second. Earth takes 365 days to go around once, our star. Mercury takes how many? 88, something like that. 88 days, 90 days to go around the sun once. And that's the closest planet to the sun. This planet, WASP 96b, goes around its star once every 3.5 days, which should impress upon you that it is ridiculously close to its star. It's like getting burnt up, basically. This is a planet around a star that's about 1,100 light years away. So it's well within the Milky Way. And this planet happens to transit its star, meaning from our point of view on Earth, it passes in front of the star. So it blocks some of the light. Now, blocking some of the light means if you're watching this star every 3.5 days, you'll see a dip in light. Simple, it's transiting. It's almost like an eclipse, but it only blocks a little bit. The interesting thing is that this planet has an atmosphere, a big puffy atmosphere. It's a gas giant, big, huge, giant, puffy atmosphere. It's super close to its star. It's really hot, puffed up. And so, yes, it blocks some of the light, but around the edge where the atmosphere is there, and you can see it right there, some of the light is filtering through the atmosphere. and coming to our detector in JWST. So what we can do is some fancy astronomy work. Basically, is we take the spectrum of the star when there's no planet in front, we take the spectrum of the star when the planet is in front of it, subtract them, and we get this. This is a spectrum of light that has filtered through the atmosphere of a planet. And as you can see, there are notable, very I want to say precise, obvious is the word I'm going for. It's very obvious that water vapor exists in this atmosphere. Woo! So that's basically one of the things that JWST was built to do, is study the atmospheres of exoplanets so that we can ask questions like, okay, there's an exoplanet. Yes, we know that it's the size of Earth. Great. But does it have an atmosphere? And if it does have an atmosphere, what's in that atmosphere? Does it have oxygen? Does it have methane? Because that would be really interesting. Or is it like Venus and have only CO2 and super hot? We can ask those questions and now answer those questions with JWST. So this was really exciting. And the most important part about all of this is that NIRISS was one of the instruments built by Canada, provided by the Canadian Space Agency. It is an incredible instrument. It's going to do some really good science, especially out of some astronomers in Montreal and some at U of T. They're across the country. And because of this contribution, Canada gets guaranteed observing time on JWST. So we have our own amount of time that we allocate as Canadians to other Canadian astronomers. It's very good. Okay, here are two infrared images of the Southern Ring Nebula. I don't know, forgive my lack of knowledge. I don't know where the Southern Ring Nebula is. I assume it's in the southern half of the sky. But I'm not 100% sure. But here are, there's a near infrared image here, and a near infrared image here, and a mid infrared image here. So these are like two different colors, to go back to the earlier conversation, in infrared. So this is, keep in mind, this is false color, right? We don't see infrared light. So we attach colors that we understand to these. What we're looking at here is actually a binary star system. You can't tell in this one, but you can tell it here. There's the two stars, one of which has been shedding its material. It's turning into a planetary nebula. It's like what the sun is going to do 5 billion years from now. And the shapes, again, we can go into a lot of detail here, but all of the structure that you see, like the ray patterns, the different shells, you can see it almost feels like there's like one shell out here, and then you can see like the faint wisps of other shells, and then there's like a bigger shell here. All of this is created by successive eruptions of the star losing its material. And for those interested, this little thing right here is a background galaxy. So that's kind of cool. It's on like an edge-on spiral galaxy. Okay. I want to get to the new stuff. Here is Stefan's Quintet. Some of you may know this one very well. Stefan's Quintet is a visual group of 5 galaxies, only 4 of which are actually bound to each other. That would be 1, 2, 3, 4. Those 4 are actually in a group, galaxy group. We use the term group in this case because it's a small amount of galaxies. Clusters are like hundreds of thousands of galaxies. Anyway, these 4, 1, 2, 3, 4 are bound to each other. They're together about 300 million light years away. And this is a foreground, well, a galaxy in the foreground in comparison about 50 million light years away. This is an infrared image again. You can compare it to some optical images from Hubble, which I should have done. And one of the interesting things they can do with this is, because it's an infrared telescope, this galaxy specifically has a black hole at the center that's doing some eating. It's an AGN, so they can do some eating there. And they can, with the infrared, we can really see tidal streams between, meaning these galaxies are interacting with each other because they're so close to each other. And we can look at the structure created when you have two things collide or go near each other. And like, for example, this big stream of stars and all this light in here, it's galaxies tearing each other apart. So we can look at it differently in the infrared. So what is that? how many did I do? 1, 2, 3, 4. And the final one was, this is the one they ended on. And I think you can see why. It has incredible colors. The Karina, you all know the Karina Nebula. And if you don't, it's one of the most beautiful nebulae out there on the sky. It is unfortunately in the southern hemisphere. So to see it yourself, you got to get closer to the equator. I don't know what its actual declination is. So I'm not sure how far south you need to go, but it is bright. It is huge, and it is a stellar nursery. Here's one thing that I thought was really interesting. How do you put a scale on this in your mind, right? Like physical size. I want to compare it to the solar system, because a stellar nursery is a place where stars are born, and therefore where planets are born. So looking at this is a big cloud of gas and dust down here, all that gas and dust. In it, stars are being born, planets are being born. So how big is this thing, right? Well, what they call the cosmic cliffs is this, what looks like a mountain range along the top here. And the numbers they gave for this is from the highest peak to the lowest valley. So like, say from like this peak, if you want to call it a peak in a mountain term, to this lowest valley here, that distance is about 7 light years. Now, in comparison to the solar system, the size of our solar system is like 1 light day, roughly speaking. So this is 7 light years from here to here. And our solar system is 1 light day. Think of the large amount, how much material is here, how many star systems you can build with such a massive cloud of gas and dust. Unbelievable. And here's the same place. This is Hubble, and there's JWST. The notable difference, JWST is infrared. This is optical. And you can, if you stare at the two of them for a minute, you can tell that in this one, you are actually looking through the dust. Whereas in this one, the dust blocks everything. So all down here, it seems much more opaque. Whereas up here, it feels like you're kind of seeing through a little bit, because infrared allows us to see through dust. Was there a question? Oh, there's a few more questions. Oh, there's lots going on. Oh, there's so many people talking. Okay, I'll come back to that stuff. Okay, today. So that was all released on Tuesday. Today, they released a couple of engineering images. Actually, they released like everything. And there's a website you can go to, and you can do Python scripts to download stuff. But they made it easy for us, and they released a few images. One, they released some images of Jupiter, because they were doing some commissioning images, trying to ensure that they can point at things like planets. Here's an image of Jupiter and Europa, right? Where is it? Right there. There's Europa. There's the shadow of Europa, by the way. And look at the precision. Look at the resolution on Jupiter here. Like, you can see the wispy, there's the red spot. You can see the structure in the clouds. Absolutely amazing. This is with one of their infrared cameras. Here is the same camera. This is with the 212 filter, and this is the 323 filter. So this is near infrared, and this is mid infrared. Here's what I'm loving about this. You can see Jupiter's rings. So look at them. There's Jupiter's rings right there. And they are right there. It's wonderful. Absolutely. So they were doing this. They were pointing at Jupiter for seeing how well they can point at solar system objects. This was during commissioning like a few weeks ago. And they also wanted to know if they could track solar system objects, because as you know, planets track or move on the sky differently than the background stars do. So it requires a different kind of tracking than tracking a star or a galaxy. So and here's I think this is an animated, this is a GIF showing it moving, because what they were trying to do is point at the background, the stars behind Jupiter, and see if they could hold on to the stars while Jupiter moved out of frame. So it's commissioning engineering work that they're doing. They also pointed it at an asteroid. And so they were wondering, they're like, let's push this to limits. What's the fastest thing that we can track? Because the sky moves in its regular movement, but what about solar system objects? So they pointed it at an asteroid, which is that one right there, I believe. And they tried to track it. And for the aficionados in the audience, they built JWST with the expectation that it could track something moving 30 milliarc seconds per second. But when they did it with this asteroid, they were able to track up to 67 milli-arc seconds per second. So, okay. So what is that? So 1 arc second is like a few thousandth of your finger width. So if you hold your finger at arm's length at the sky, just take like a little 1,000th of that, and that every second they're able to, roughly speaking, this is like very roughly speaking, the precision is a lot higher. It's actually 2 times higher on the tracking than they thought they could do. So they're not great images, but they show you the engineering that they were doing. And there you go. I'm done. That was like 2 times longer than I wanted it to be, but I hope you enjoyed it.
Jesse, you're more than welcome. I too feel like you do. When I first saw the lensing image from the release on Tuesday, my first thought was that there are dozens of careers to be had simply in the interpretation of the detail in those Einstein arcs.
Yeah.
And so, yeah, we're all gobsmacked. I like to take the initiative of asking the first question. There's been lots of chat, but as a specific question to you, as an old quasar guy, what are you looking forward to?
Oh, well, I've thought a little bit about this. So the interesting thing about AGN is trying to develop a model of the structure, because quasars, so AGN in general, there's nearby AGN, commonly sometimes called Seyfert galaxies. And then there's the quasars, the high energy ones that are really, really far away. And you don't resolve a quasar. Quasars don't, they're so far away. They're halfway across the universe, billions of light years away. So we see this light coming from a quasar, and it's hard to develop structure. It's hard to develop understanding. When I look at a quasar, I'm using optical telescopes, and an optical telescope is when I'm looking at a quasar with an optical telescope, I'm looking at redshifted light. It's billions of light years away. So the light that I'm actually seeing was UV light when it left that quasar. So when it gets to me, it's been redshifted into the optical. Now, if I'm bound by my optical telescope, if I'm bound by the ability of what an optical telescope can do, then that means I stop seeing, there's a dropout area. When I get past the red, when the light that I'm interested in seeing has been redshifted out of the optical into the infrared, then I can no longer study those objects. They're too far away for me to study. So with an infrared telescope like JWST, with such incredible, unbelievable resolution, we're going to be able to see quasars even further back and maybe get a good sense of how they develop, because a quasar seems to be an evolutionary portion of a galaxy building where it goes through a quasar phase. It's almost like an adolescent phase or like a teenager phase. It happens only in young galaxies at the beginning of the universe. So how did that ramp up at the beginning of the universe? We're not really sure. And having such a powerful infrared telescope may help us learn about how they get started and their structure with the infrared. So that's what I'm going with.
Okay, and now that I've done my bit, thank you. I'm sure there's got to be other questions out there.
Okay, we got
in the Q&A.
Why is it important to keep the camera cool to image in the infrared? Because I think Tim has answered it, because the infrared, we experience it. We don't see infrared, but humans can experience portions of the infrared as heat. And so you have to cool these cameras way down, so that heat from the cameras doesn't affect the light you're observing. We also employ the same techniques with regular optical cameras as well. You cool those cameras down, but they don't need to be nearly as cold as an infrared camera does. And Gerald answered that. Yeah. Southern Ring Nebula, NGC 3132 in Antilla. Karina Nebula is minus 59. Okay, you got to get down there pretty good to see it. The shape of the Karina Nebula has changed, is it? Oh, you know what? Tim, no, who said Gerald? Just the shape may be different, but that's could be related to you're receiving light from different regions slightly because it's optical versus infrared. So you could see shape differences just based on looking at it in different lights. But it also may have changed because it's probably a turbulent thing. And that's all of it. That's all the questions from the chat box.
Okay, so before I let you go with our thanks, Jesse, I do have one point to raise, and that is to chastise you over saying that how unfortunate it was that the Karina Nebula was so far south in the southern skies, because from my hometown, it was almost directly overhead. And so I say to your sense of the unfortunate, but thank you very much.
I'm so sorry. A very good friend of mine, Paul Delaney, is himself Australian and constantly chastises me for having such a north frame of mind. So thank you for keeping me global.
You mean boreocentric. So anyway, look, I'm sure we'll be getting you back as more of the data and more of the interpretation comes out. And I hope you're amenable to further return visits. Absolutely.
I'm looking forward to two things: exoplanet data, especially terrestrial planets and seeing their atmospheres, and then quasar work. So I'll look. I'm going to be watching for when that stuff comes out, and I'd be happy to come back and chat about it.
All righty. So thanks again, Jesse. Job well done, and we'll see you soon, I hope.
Great. Yes, absolutely. Thanks for having me, everybody. See ya.
And so, Chris, let us move along to the other end of the cosmic scale. Simon Hanmer, well known to many of the members. For those of you new here, he's not even a proper astronomer. He's a bloody geologist. But over recent years has managed to meld his interest both in planetary geology and amateur astronomy to keep us constantly entertained with his updates on the state of the science on particularly solar system issues. And so, Simon, please, over to you for your update on the last year's worth of developments in inner solar system science.
Okay, Mick, I need Chris to stop share. There we go. I can share mine. Can you see it?
Got it.
Okay, let me just bring it up to full blast. There we go. And I need to get rid of, there we go. So that I can actually see my screen, get rid of me. Alrighty. Oh, and the one other thing I need to do before I start, I need to go to annotate Spotlight, and I believe this is the one. There we go. Now I can actually show you what I'm pointing at. Okay, well, here we are, a week late, but not to worry. There's not been too much came out this week, which has really changed the nature of my talk. Solar system science. Solar system science is advancing at an ever-increasing rate, some of which I've brought to your attention over the past 20-odd years, as Mick pointed out. And during the past few years, I've presented an annual update on the thinking of professional planetary scientists. And it's time to bring you up to date on the solar system thinking for 2021. Now, let's be clear. This is the year when the papers would have actually been published. The thinking would have been going on probably for the decade prior to this. But that's just the way that the scientific publication world works. Now, the trouble is, this year, there's so much that I could tell you about, and not all of it would be of interest to amateur astronomers. There's a lot of stuff that's, well, rather esoteric out there. So tonight I'm going to limit this talk to the inner solar system. In other words, Mercury, Venus, Mars, and of course, the Moon. And I need to... Nope, well, went too quickly. There we go, there we go. Now, however, this year we have some help, which is freely available on the web from the National Academies of Science in the United States. They've just released a comprehensive report entitled A Decadal Strategy for Planetary Science, 2025 to 2032. In other words, it's forward-looking for the decade. But they present summaries on all aspects of solar system science over the past, what they call transformational decade, from planets to asteroids. And it's well worth looking at, even if you only glance through it diagonally. At the very least, it's worth going to the Sky and Telescope link, which is actually shown here. Got it up there. I'll talk to you about that in just 1 second. And reading their summary of this decadal strategy. Now, I want to point out that on the series of slides that I'm going to be showing you, there will be internet links. No, I'm not asking you to copy them down. You can actually find my presentation and all of the presentations that I've given over the last 20 years on my personal website, which you can get to through the RASC Ottawa website by going to the Educational tab, or the Education tab, clicking on that, and then Planetary Science, and it'll take you to the page in my website that has these presentations. So don't worry about having to write down these links that I'm going to be showing you. So for each of the rocky planets, this decadal strategy provides a short list of what the authors consider to be key discoveries. So for each of the rocky planets, my plan tonight is to compare the decadal strategy short list of key discoveries with my own perception, and I emphasize my own personal perception, of key points of personal interest, that was a little Freudian slip, of potential interest to amateur astronomers such as RASC members, stemming from publications that saw the light of day during 2021 and the beginning of 2022. So let's start here with Mercury. And according to the Decadal survey, the key discoveries of the past decade include, there are others, but I just wanted to pull out the key ones, the presence of abundant volatiles in the planetary crust. It's a bit of a surprise given how close it is to the Sun. The detection of a very weak magnetic field, wasn't expected. Water ice in permanent shadow areas in impact craters at the poles. Again, I don't think anybody would have predicted this 20 years ago. And then the decoding or the geological understanding of the surface volcanism. Now, I don't disagree with any of these points. They are indeed key discoveries. But I think you could restate some of them in a more exciting way to grab the attention of amateur astronomers such as ourselves. For example, instead of just talking about volatiles, how about talking about diamonds? And planetary crusts may be made of diamonds. Here again, you'll see a URL, which will take you to a link, which is more or less readable. Now here, just below it, there are two quotes. They're direct quotes from this extended abstract, which is referred to here with my URL. These direct quotes, which give from this abstract, which was given at a recent science meeting. Let me just read these two to you. Diamonds in meteorites. New work shows conclusive evidence for impact shock transformation. And the second one says, Mercury may be unique in the solar system in having formed a graphite flotation crust during magma ocean cooling. So if we pass the first statement, that's P-A-R-S-E, by the way, it says that we know diamonds occur in some meteorites, and that new laboratory work indicates that some of those diamonds could form by the transformation of carbon, probably graphite, into diamond due to high pressures generated by bolide impacts. Now, the second statement tells us that of all the planets, Mercury may have had a crust of graphite scum that floated on top of a primordial magma ocean soon after it first formed by accretion. Now, this means that the crust of Mercury may contain diamond. Now, not necessarily the jewelry kind, as you see here. Probably far more likely rough diamonds, such as you see here on the right, or even more likely microdiamonds or diamond dust. Now, the paper then goes on to suggest that, hypothetically at least, outside of our own solar system, this process of impact transformation could result in planets with crusts made entirely of diamond. That, I think, is an exciting concept. Now, other features related to crustal volatiles on Mercury are referred to as hollows, and they're quite spectacular. They tend to occur on the floors of impact craters. Here's an impact crater on Mercury, and the hollows are these blue things here. This is a blow-up of this rectangle. And I want you to notice the scale bar. It gives you an idea of the size of the crater and the size of these hollows. They're reasonably big. They do not themselves have raised rims, unlike the craters themselves. And so they're thought to be collapse features that formed holes when buried volatiles, which were in the mercurial crust, sublimated into space. Remember, Mercury has no atmosphere to speak of. This is a close-up on what you would see in here. And you can see these pits here. They really are flat-rimmed. And again, you can see the blue of these volatiles. In fact, there's the very real possibility that these hollows are not only very young, but they might even be forming today. In other words, these volatiles may be dispersing into space as we speak. Neat. However, what is the sublimating volatile made of? Now, there are two main candidates. One is carbon compounds, in other words, graphite, plus all kinds of other stuff mixed in with it. Probably sulfides, something rather like fool's gold, for example, or pyrite. And the other option is pure elemental sulfur, just sulfur with nothing else, the yellow stuff that you see around volcanoes, which is interesting. For various reasons, carbon compounds are not the best candidates for these volatiles. I won't get into that. But it turns out that if you want to get the elemental sulfur to sublimate, you need to give it an extra thermal kick to get the buried sulfur to sublimate into space and make these hollows, these holes. So some clever folks who published a paper, which again is referred to up here, they suggested that when a bolide or a meteorite makes a crater on Mercury, then beneath that crater, the impact generates extra heat, which then mobilizes the buried sulfur that rises along fractures. Here's the crater, there's the central peak, there are fractures along the margins, and the idea is that the mobilized sulfur rises along these fractures toward the surface, where it then sublimates into space at small volcanic centers called fumaroles. And fumaroles really comes from the French word smoke, fumée. And we find these fumaroles associated with volcanoes on Earth. So this way, they explain the relationship between the hollows and the impact craters themselves. Why do they form in the impact craters? Because of this mechanism. Now, many of you will be well aware that Mercury is an oddball planet. It's an oddball essentially because its metal core is way out of proportion to the size of the planet as a whole. If you look at your average differentiated rocky planet, such as here, the core is relatively small compared with the mantle and the crust, but not on Mercury. Mercury is a different kettle of fish. And this has long created major problems for the overall model of how rocky planets form by accretion of primitive chondritic material, as it's called, and how this differentiates eventually from a homogeneous mass into core, mantle, and crust. And we can see bits of core, mantle, and crust from space. This is what a chondrite would look like. But we get stony meteorites, and we get iron meteorites. The irons resemble the cores of planets, and the stones resemble the crusts. I'm not going to talk to you about the mantle for the moment. So there are all kinds of theories to account for why Mercury has this huge crust here compared with the size of the planet as a whole. And these range from a massive impact that stripped away much of the original mantle of a once much larger Mercury, to an anomalous iron-rich composition of the innermost accretionary disk from which all of the planets and the sun formed. Now, all of these hypotheses have major problems. For example, Why would the innermost solar disk be so iron-rich in the first place? Well, now, recent work, again, you can find the URL which would take you to the story of that recent work, suggests that it's all down to the sun's magnetic field. Since that magnetic field is stronger the closer you get to the sun, it turns out that it attracted the iron which was dispersed throughout the original accretionary disk towards the sun. And what planetary scientists have done to arrive at this conclusion is they've compared the cores of all the rocky planets, rocky bodies in the inner solar system. You can see this diagram here. This would essentially be a measure of the amount of iron. They've actually used solid density to do this, and this is distance from the sun, close in, further away. So you can see Mars, the Earth, Venus, Mercury. And you can see this line that runs through, highlighting the fact that the amount of iron in the rocky bodies does indeed increase the closer you get to the sun. This is proportionally speaking, of course, because the planets and the cores are different sizes. So they're looking at the different amounts of of iron in proportion to the size of the planetary body. This is certainly as good as any other explanation that's on the table to date. So, okay, let's turn to Venus. Now, according to the Decadal survey, the key discoveries in the past include, again, there are others, recent and maybe ongoing tectonic and volcanic activity, and, of course, potential habitability, perhaps having lasted for billions of years. Now, again, while I don't disagree with this, I think some new perspectives are of more direct interest to amateur astronomers than others. For example, this habitability question. There's a very interesting ongoing debate right now about whether or not the first 3 billion years of Venusian history might have involved a wet, habitable environment, even with an ocean of water. Now, it's fascinating stuff, but it's all about rather complicated chemical considerations, complex atmospheric circulation and planetary orbital calculations and what have you. And it's difficult to get into without a lot of background knowledge. On the other hand, there was phosphine. Remember phosphine? Phosphine is a simple compound of phosphorus and hydrogen, and it may have been detected in the upper atmosphere of Venus. Maybe. There are serious doubts. It can be the product of organic metabolism, for example, by bacteria, but it can also be the product of inorganic volcanic activity. The initial suggestions that phosphine indicated bacteria floating around in the upper atmosphere of Venus were unconvincing, to say the least. I don't mean to me, I mean to the rest of the scientific community. So folks then turned to trying to explain Venusian's phosphine by volcanism. However, as the two direct quotes you can see here and here from a recent extended abstract in this topic show, there's a problem. This is how you get to that abstract if you want to read it. So let's read these two and pass them. It says volcanically extruded phosphides, that's the phosphine, as an abiotic source of phosphine. Sorry, let me pass that again. Volcanically extruded phosphides may be an abiotic source of Venusian phosphine. And the second statement says, yeah, but only extraordinary volcanism can explain the presence of even parts per billion of phosphine on Venus, by which they mean in the atmosphere. In short, apparently you would need far more volcanic activity on Venus than we can justify with the current knowledge in order to produce even minute traces of phosphine using volcanism. And people aren't too keen on this bacterial idea either. So in short, if the phosphine is really there, which we still don't know, we're not sure why. Given the fuss that was made about phosphine last year, that's quite an important conclusion. So still on the topic of volcanism on Venus, there's a strong set of arguments in favor of the idea that some volcanic eruptions on Venus might be very young, and they might even be ongoing today. So again, let's pass these two direct statements taken out of this Sky and Telescope summary of this story. Now, The first one says chemical weathering. That's the alteration of surface material through chemical reactions with atmospheric gases. Happens more quickly than previously thought. This is important. It's not a slow process, they're saying. It happens even faster than they had thought. And here's an important statement. Unusually high thermal emission, let's not worry technically as to what that means, it's basically infrared, indicates that the surface of this particular volcano hasn't yet been corroded by Venus's caustic atmosphere. Now, let's just see what that actually says. The second statement is saying that new evidence and calculations indicate that even under the conditions of the Venusian atmosphere, hot as it may be, the chemical alteration of volcanic rocks should happen very quickly, and yet it hasn't. However, the second quote, sorry, I got that one the wrong way around. That's the first quote. The second quote is saying that the geophysical readings from orbit indicate that the surface of the major volcano on Venus must be made of uncorroded rock. And when you put the two ideas together, you have to conclude that there's some very, very young lava sitting on the slopes of this volcano, because otherwise, by any measure, they would have been corroded and haven't been. So I don't see any way around the idea that volcanism on Venus is very young and may, in fact, be happening today. Now, another Sky and Telescope article, again, you can see, find the, I guess this must be an astronomy article. Either that or I've got the wrong URL here. I'll check that and I'll correct it for when I post the presentation on my website. An article, it reports on a recent paper that claims to show that the surface of Venus might be tectonically active, including perhaps at the present day. Now, the authors of the scientific paper claim that complex bands, which are shown in yellow in this image here, represent zones of strongly deformed rocks which have been transformed by the jostling of these large, smooth purple blocks between them. And by jostling, they're envisaging an analogy between these crustal blocks and jostling sea ice. That's what they specifically refer to. They go on to suggest that this might indicate what the early Earth might have looked like before the establishment of modern plate tectonics. Now, it's an interesting idea, but those yellow zones are very, very wide. They're 100 to 200 kilometers across at the surface of the planet. And this is an order of magnitude wider than I would have expected from examples we know of from Earth, of slipping and sliding zones. And let me just point out that I spent 40 years of my career actually working on slipping and sliding zones on Earth, and I can tell you that they would not normally form like this anywhere near the surface of a planet, ever. However, it's an idea that's already seduced many in the planetary science world, and it figures prominently in the Decadal survey, so don't be surprised to see that. So turning now to the Moon. According to the Decadal survey, the key discoveries of the past decade include a global gravity survey that highlighted buried structures, new chemistry that challenges the lunar origin models based on physics, high-resolution imaging by the Lunar Reconnaissance Orbiter program. I've shown you pictures of those in the past. They're astounding. And again, water ice at the poles. All of these are indeed transformational discoveries, and I've already talked about some of them with you during these meetings in the past. But tonight what I want to highlight are aspects of the Moon that are visible to us as amateur astronomers, starting with a hypothesis to explain the difference between the lunar near side and far side. In a recent paper summarized in Universe Today, again, there's the URL, and yes, this is the correct one, suggests that the difference, called a dichotomy, might be explained by the effects of a massive impact in the early lunar history. And that impact would be represented by the South Aitken Basin here on the far side of the Moon. And that's what the South Pole Aitken Basin looks like in gravity data. Now, the idea here is that the impact would have generated a wave of heat that would have mobilized a massive plume of molten rock that would have swept through the entire lunar interior to the other side. And this plume would have swept up all kinds of heat-producing elements from the lunar interior and carried them and concentrated them to the near side, especially in what's known as the Prosolarum creep terrain, which is this area here. And this contains many of the major impact basins. You can actually see this image of the moon up in the top right corner. Contains Imbrium, for example. Imbrium would be right there, just to place it for you. And this extra heat would have contributed to forming the massive volcanic plains that we see on the near side as the dark lunar mare. And that would have allowed that volcanism to continue through to 2 billion years. That's really important because at about 2 billion years, the far side was already dead and cold. So this explains, to a significant degree, the difference from one side to the other. Now, a lunar feature that many astronomers, amateur astronomers, enjoy observing on the moon are what are called swirls. Many of you will know Reiner Gamma, which is probably the most famous on the left side of the moon, approximately in equatorial latitudes. These are light grey patches. They're very irregular and swirly in shape, and they've long defied a robust explanation. Some have suggested that they represent dust caught up in local magnetic fields, but that explanation isn't quite enough. There's something missing from the explanation to really account for what we see. Now, thanks to very high resolution topographic altimetry, recent stuff, a new paper has shown that the light swirls occur in very shallow depressions, just a few meters below the local lunar surface. So you can see this gray area here. This, by the way, would be this blown up. The gray here is the swirl. You can see the medium to darker gray of the rest of the lunar surface. And these are contours, this being low terrain and this being higher terrain. But we're talking about a difference in vertical height of a couple of meters. But the important thing is that those depressions, even if they're very, very low amplitude, they're enough to trap the swirling dust that's caught up in the magnetic fields. So for the first time, we now have a possible mechanism for trapping the dust after it's become mobilized. And in fact, this has led some researchers to suggest that this indicates that the lunar dust may be even more generally mobile than we thought, which of course is going to be problematic for long-term occupation of the lunar surface. So, okay. We've looked at dark lunar mare and light lunar swirls, but what are folks currently thinking about all the white stuff, the anorthosite, that makes up the lunar highlands? Now, a very interesting idea is encapsulated in the two direct quotes from a recent paper summarized in Universe Today. There's the URL. And here are the two quotes. The age of the anorthosite highlands does not match how long it took for the moon's magma to cool. And the second one says, rather than taking 100 million years to cool, the magma ocean was a slushy mix that took over 200 million years to cool. So recall here that the general idea is that the white feldspar that makes up the bulk of the anorthosite that you see even naked eye looking at the moon represents a low-density mineral scum that floated to the top of an initial magma ocean early in the lunar history. And that's what's illustrated here. A completely molten magma cools down, and this anorthosite crust forms on top of the magma, and the heavy stuff falls to the bottom. However, the first statement that I read out says that if you calculate how long it would take for that uniform 100% liquid magma ocean to cool, it's much shorter than the range of crystallization ages which we've actually determined from samples brought back by the Apollo astronauts. Only 100 million years, whereas it turns out that the specimens brought back suggest that it was cooling for 200 million years. However, some clever folks redid the calculation by assuming that instead of a 100% liquid ocean, the ocean was in fact a convecting slushy mix of crystals and liquid, all cooling together. And it turns out that this extends the cooling time, which you can see on the right. That's what this model here is here. This is the slushy mix or convecting and cooling, it extends it by enough time to cover the full range of the anorthosite crystallization ages. Not bad. Not bad at all. Okay, let's move beyond the Earth and out to Mars, our last rocky planet tonight. According to the Decadal survey, key discoveries of the past decade for Mars include the presence of organic compounds, I put that in inverted commas, water ice at temperate latitudes, habitability, almost inevitable now, and Mars quakes and modern geological activity. Now, although at first glance these points all seem valid, I beg to differ on 3 of the 4 of them. On the one hand, recall that the organic compounds are not organic materials, i.e. they're not the products of life. And they've been known from interstellar space for quite some time. They're actually the building blocks of life. That doesn't mean that they've been put together organically. It means they could come together to form things organic. I'm somewhat concerned about the use of vocabulary here. Water ice at temperate as opposed to polar latitudes is not a scientific breakthrough. We've known about glaciation features at these latitudes for decades. But both of these key discoveries are part and parcel of NASA's never-ending habitability communications mantra about eventually finding evidence for life on Mars, even if it's extinct. I'm sorry, but I find that this mantra grows wearisome with time. On the other hand, the Mars quakes are a different kettle of fish that I'll get to in just a minute. That said, I think there are several recent discussions that will readily grab the attention of amateur astronomers regarding Mars. For example, what about the planet-scale dichotomy between the northern plains, shown here in blue, they're low, that's why they're blue, topographically low, and the southern highlands down here, which are in the yellows and oranges and reds because they're high, and the whites. Some of our RASC members have actually successfully observed and imaged this topographic dichotomy. In a recent book, Mars Geological Enigmas, published in 2021, you can actually get to the abstracts for the articles through this link here. There are 2 papers that deal with this topic. One reviews what's called the exogenic impact hypothesis, in other words, something coming from outside of the planet and smacking into it, and the other reviews the endogenic plume origin for the dichotomy. In other words, some major masses of hot mantle rising and then spreading at the surface to create this lowland terrain. Now, I've highlighted 2 statements from these papers. The first one simply reminds us that the debate is ongoing. There is no agreement to date. And the second one emphasizes a problem with the impact hypothesis. What it actually says is that there should be a thick ring of basin ejecta at the rim of the northern plains. It should be all the way around the rim of the northern plains here, and that it should thin according to a predictable pattern which you can calculate as you move away from the lowlands and onto the highlands. And it simply is not there, inconsistent with current observations. Does this mean the endogenic plume hypothesis, which is the one on the right here, is correct? No, it doesn't, but it does leave it as the last standing contender, for the moment at least. For the past few years, there's been a lot of talk and speculation regarding the presence of lakes of liquid water on Mars today, beneath the southern polar ice cap. Now, let's be clear here, no one has seen water. But some get very excited because where there's water, there's life, to quote that NASA mantra. And the evidence is a bright reflection in ice-penetrating radar that's been interpreted to represent lake water. And you can see that represented here, the idea of liquid brine down here. There's the ice of the polar cap, and radar from orbiting satellites looks through and gets a reflection back, which has been interpreted to represent water. However, the second statement says other materials than water, like salty ice and clay, could also produce the bright reflections. And that, of course, is a quote from this paper here. So it's calling this simple interpretation into question. And if it turns out that clay, specifically a clay called smectite, or even just salty ice, not melted, can produce pretty much the same radar reflections, then, well, I don't know, maybe present-day lakes on Mars, maybe not. A lot less clear than we thought. Okay, so finally, what about the hypothesis? No, not finally. The hypothesis that the northern plains were once covered by an ocean of water. A decade ago, this hypothesis appeared to be strongly supported by the purported distribution of river channels cutting along, or rather across, I'm going back one here, river channels cutting across this dichotomy boundary and the location here of deltas. And I discussed this in some detail with you in 2012. However, two recent papers call this line of evidence into question, and they are both identified here. And the first is a global review of deltas that concludes that many of them may have actually been misidentified and that they're actually something other than deltas. I won't get into it, but whoops. The second paper examines the purported ocean shoreline itself in some detail. Now, it's long been known that the purported ocean shoreline does not follow a single contour, topographic contour. In other words, single sea level. So if it exists, it must have been physically disturbed after it formed. In other words, tectonically disturbed. Now, here's the problem. The calculations show that Jezero crater, which is where the Perseverance rover is actually wandering around over a delta, a classical delta system, it turns out that the Jezero crater would have been well under the ocean water, whatever model of physical disturbance of the supposed ocean shoreline is employed. And that's illustrated here. This is one model for calculating the disturbance of the dichotomy boundary, and this is another one. This is Jezero crater in both cases, and the blue indicates modeled ocean water. Here's the problem, is that deltas don't form under oceans, they form at the water's edge. So the point being made here in this paper is that the ocean model is incompatible with deltas at Jezero crater at the time the ocean is supposed to be there. Does this eliminate the ocean hypothesis? No, but it does complicate matters. So, what's new with respect to planetary science? Now finally, and this is finally, at last we come to what I personally think is the most interesting new news regarding Mars over the last year. The seismological data from InSight. InSight is a single stationary seismic recording station on Mars. It's at a huge disadvantage because it's only one, and without at least three, it's difficult to triangulate and get a good position for anything actually happening to generate seismicity. But 3 new papers have just been published in Science magazine, and I give you the access to their abstracts here. And although there's only one seismic station, planetary scientists have already observed, or actually, yes, observed, some excellent results at the scale of the planetary crust, mantle, and core. On the left, over here, you can see what the data look like, and some of the initial interpretations. Don't look too closely. It's pretty complicated stuff. I'll just show it to you so you'll know that there actually is data. But if we try to keep it simple, what do the seismologists think is new? And that's more what we can see here. This is their interpretation. They think that the Martian crust turns out to be pretty thick in places, way thicker than they thought it was going to be, and now they actually have some measurements. The Martian mantle, which will be between the core and the crust, it turns out to be a single layer, according to the seismology. Unlike the Earth, where it's divided into 2 layers, an inner mantle and an outer mantle, with serious consequences for how the planet behaves. And the Martian core, as you can see here, is actually relatively big. It's not as big as Mercury's crust, or his core is with respect to the planet size, but it is large, and it's entirely molten. In other words, it's doesn't seem to be divided into an inner solid and an outer liquid core. That was a surprise. So these are not bad results for a single seismometer. So, what's my take-home message tonight? Well, I've shown you what the decadal strategy thinks is key in recent planetary geology, at least for the rocky planets of the inner solar system, and what I think would be of special interest to RASC Ottawa members. So I've added here, there it is down there. There's the URL link to the decadal strategy document itself, if you care to look at it. It does get a bit dense and jargony in places, but there's a lot that's accessible to the interested amateur, such as yourselves. Download it. Scan it diagonally. Just go through it diagonally, only pausing at places that particularly interest you. Meanwhile, keep your eye out for amateur-oriented summaries in Sky and Telescope, Astronomy Magazine, and Astronomy Today, all of which are available on the web and quite approachable. And let us know what catches your eye in the solar system science. As always, thanks for listening.
And as always, Simon, thank you for bringing us up to date. And again, I will use my chair's prerogative. I do have a question for you. And I've been fascinated by this for going on 50 years now. The Calorus impact basin on Mercury and its antipodal freakish terrain.
Yep.
You then describe the South Polar Aitken Basin and the Procalorium Crete Plains.
Mm-hmm.
What is the current thinking of any relationships, similarities, analogies between those sets of formations?
That's a really interesting question. The Chinese, let me get this one straight. No, the Chinese are on the other side. The Chinese, I believe I'm right that they have a rover in the South Pole Aitken Basin and have been looking at the surface material. It's either that or I'm confusing that with an orbiter that's been analyzing it. But what we know is that what's in the South Pole Aitken Basin looks like mantle material. In other words, the impact, not only, according to this hypothesis, would have driven a wave of heat, scouring material and moving all the way through the moon to the other side, but local mantle material would have come up and actually covered what would have been the surface of the impact basin. On Mercury, it's a different kettle of fish. On Mercury, it's basaltic lavas. They're probably a lot less thick than what is covering the South Pole Aitken Basin. All that people would be able to do is basically hypothesize, because I think that you find that certainly the South Pole Aitken Basin is pretty well resurfaced by whatever came up from below. So I don't think we can actually draw direct analogies between the chaotic terrain on Mercury, because that chaotic terrain is itself. Thank you, Brian. It is a Chinese rover. The chaotic terrain on Mercury is not flooded by more recent volcanics.
Okay, so issue remains open. Are there any other questions that people would like to put into the Q&A before we let Simon go? Okay, if not, again, thank you, Simon. We'll see you for your 60-second presentation sometime soon, I'm sure. And with that, Chris, I think it's over to the bio break. And so, trivia question. True or false that trees on Earth outnumber stars in the Milky Way? Yes or no? Ponder that for the next 5 minutes and we'll see you shortly. Thank you.
Yes, I am.
Alrighty. So, first, I will dispense with the trivia question. Then we pass back to Simon for a latest update on his answer to my previous question. True or false? Trees on Earth outnumber stars in the Milky Way. Chris? They do outnumber stars in the Milky Way by about 10 to 1. Obviously, these are estimations, but still, that is a lot of trees compared to a lot of stars. Thank you. Okay, back to Simon.
Okay, Chris asked me, Mick asked me about the possible analogies between the formation of the Caloris Basin on Mercury and the formation of the South Pole Aitken Basin on the Moon, and pointed out that on the other side of Mercury, there's this chaotic terrain which has been highly disturbed by the results of as a consequence of the major impact that formed the Caloris Basin. On the Moon, that chaotic terrain would have been sitting where we presently see the major lunar mare, for example, the Imbrian Basin. We know the Imbrian Basin and its associated basins are younger than the South Pole Aitken Basin, and they're filled with all the magmas that formed the lunar mare themselves. Why would that magmatism have occurred after the impact due to the South Pole Aitken Basin? Because it was the radioactive material which was concentrated on that near side of the Moon, which would have been taking its time to heat up and cook things up and resurface that part of the Moon. So where you might have had the equivalent of a chaotic terrain due to the impact on the far side of the Moon, forming the South Pole Aitken Basin, since that impact, you will have seen the major impacts which formed the major mare basins that we see even naked eye on this side. And we would then resurface those with these huge outpourings of lava. In other words, if there was chaotic terrain, it's below or has been reworked by the major mare basins that we see on the near side of the Moon. That is the correct and clear answer to Mick's question.
All righty. Thank you. Appreciate it. Chris, next speaker will be Rick Wagner on the RASC Astro-imaging certificate exercises. Again, for those of you who are new here, Rick is certainly one of the long-serving members and providers of material. The oldest of his I found is from 1978. So he's been at this for quite a while. And he's one of our few astrometrists who has been collecting tens of thousands of images of RR Lyrae stars over those decades. So as an advocate for the RASC observing certificate programs, here's Rick on the Astro-imaging certificate. Thanks.
Well, good evening, everybody. About 6 years ago, the RASC implemented the Astro-imaging certificate program to try and encourage members to get into astronomical imaging. And last week, or a week or two ago, I was actually preparing to make my submission for the Deep Sky certificate. And I noticed on the RASC website that only 5 certificates have been issued to Ottawa members, and 60% of those are mine. So I thought it would be a good idea to give a short talk on each of the certificates to try and encourage you all to participate. It also has the additional benefit that I get to show all the images that I submitted for each of the certificates, which is far more images than I would be allowed in the observing section. Next, please. So in short, there are 3 different certificates: the Wide Field, Solar System, and Deep Sky. And if you go to rasc.ca/astroimaging certificate, you can get all the details on what's required, download the application forms, and also see a list, a somewhat out-of-date list of those who have already received the certificates. For some reason, it hasn't been updated in about the past year. But also at RASC Astro-imaging.zenfolio.com, even better, you can see all the images that have been submitted by past recipients. Then I should mention that these certificates are only available to RASC members. So the first one I wanted to start with, next slide please, is the wide field certificate. And it's probably the easiest, certainly the one that requires the least amount of unusual, i.e. expensive astronomical equipment. And it's also one which I think is most generally interesting to the largest number of people. I mean, who hasn't taken a picture of a close pairing of the moon and a planet in the twilight sky or aurora on the northern hemisphere? And these images also show views which are sort of more easily identified with by the average non-astronomer. Now, it is the one that requires the most pictures to satisfy the requirements. On the other hand, each of these pictures can generally be a single snapshot rather than a stack of multiple images or video frames followed by elaborate processing. Next slide, please. So the goal is to have the astro-imager embrace an ethic of quality. The requirements specifically mention sharp focus, good composition or framing, and correct exposure to not lose the important details to either underexposure or overexposure. The submission has to include a broad range of subjects, and the focus is primarily on what they call skyscapes. So this is an image of the night sky with foreground, horizon or something in the foreground to give it sort of some context. Next, please. So the requirements, you have to submit 15 images from a prescribed list of 22 possible subjects. They should simulate a naked eye view or at most a binocular view. And in keeping with the idea of the skyscapes, 10 of the images should include foreground like the horizon. For each image, you have to document your equipment and settings, the location, date and time, and any planning you did, problems encountered, interesting circumstances, etc., things that make an image particularly interesting for you. Next slide. So here's the 15 images I submitted. Let's see, this one is a sunrise, obviously. This one, I was imaging all night with my telescopes, and as I was out shutting one of them down, I noticed the first twinkles of the sun through the forest down at the end of the lake. So fortunately, I had the DSLR on the scope and just grabbed a few shots. This image, clearly a very young crescent moon. This is actually taken from Majors Hill Park, looking over Gatineau, the Place du Portage towers and so forth. This one I actually shot on my way home from work. I expected that it was supposed to be clear and the very young moon was going to be visible. So I was working in the market at the time and just stopped in Majors Hill Park on my way home. And that's Venus up and to the left there. Next, please. So new moon with Earthshine. Now, you'll notice this also has two planets in it, Venus and Mercury. The three of them setting over a cottage across the lake from me. So this is actually an image that could have fit in several of the different categories. So sometimes you have to kind of pick which one you want to use an image in. Next, please. So moon and a planet. This is a view of the rising crescent moon over the frozen lake. in the dawn sky. Venus is poking through the cloud on the lower left, and Saturn is up and to the right in the northern reaches of Scorpius. My notes for this shot remark on the difficulty I had of getting an image with both the planets visible, as one would pop out and then it would disappear as the other one popped out. And it actually took me about 10 or 15 minutes waiting before they were both visible at the same time. Next, please. So 2 or more planets. This was the recent Christmas conjunction of Saturn and Jupiter. Took this from the parking lot at Old Fort Henry in Kingston. So that's Kingston in the foreground. My wife and I just happened to be in town shopping that day. And as you do when you're out shopping, I had a camera, tripod, 2 telescopes, eyepieces, all in the car, just ready to go in case something happened. It was howling windy and cold up there, but the images were very much worth it. Next, please. A picture of Mercury with the brighter Venus beside it. This is actually one image pulled out of a time lapse of the 2 planets setting. This is that same cottage down at the on the neighboring point. Unfortunately, they leave the lights on all the time, so I'm stuck with them in a lot of my pictures. So yeah, just pull one image out of several hundred that I took to do the time lapse. Next, please. So this is a pass of the International Space Station. Generally a relatively easy thing to do, except that in this case, the sky was not actually all that dark yet, and somewhat slightly cloudy or hazy. And so it was very difficult to judge the exposure so that I could take a long enough exposure to catch the whole trail without overexposing the sky. So I think I was pretty successful. Next, please. Star trails. This is from quite a few years ago. This is taken from my deck. And this is an all-night set of star trails, camera mounted on a tripod, and just taking, I think, 1 minute exposures for about 6 or 7 hours from dusk till dawn. You can see I captured a couple of meteors. And what I really like about this shot is the star colors, how well they show up, and also the fact that you can see the stars are going in a circle around the North Pole in the upper left and going in different circles around the South Pole in the right, lower right. Next, please. We had some thunderstorms going by south of us one summer evening, and I was hoping to get some nice lightning pictures, and was down on the dock shooting, and realized that this one had a nice view of the Milky Way in it with the dramatic lightning lit clouds below it. So I thought that was a nice and dramatic picture. Next, please. This is a constellation shot, obviously Orion. And this is one case where I did, in fact, do the whole business with multiple images and stacking. So this is 10 67-second exposures on a barn door tracker. And one thing I really like about this shot, it was just the thinnest of cirrus cloud created the beautiful colored halos around the brighter stars to really emphasize the star colors. Next, please. Sun or moon halo or sundogs. Well, I managed to get a whole bunch of stuff in this one. Again, my wife and I were in shopping. She was in Winners. I was sitting out in the car wondering what to do with myself when I noticed this halo. And I was able to take 2 pictures with the cell phone standing directly under the street light so that it would obscure the sun, and then combined the 2 images later in Photoshop. Next, please. The solar eclipse in 2017, we drove out to Nebraska, and I took a series of images from 125th of a second up to 1 second, and then manually aligned them all in Photoshop and faded and erased and messed around with them to get this composite image. So it was several hours work for this one. And you can see this is probably a binocular view of the eclipse. Next, please. This is Comet Neowise from two years ago. This is out from an island out in the lake, looking back over our house. Our house would be just on the right-hand edge in the trees there. Very still night at I think about 3 or 4 o'clock in the morning. Managed to get some fishing in while I was out there shooting. Next, please. Meteor Shot. So this is actually from a time lapse I did of the Geminids in 2017. And what I did was I took the 5 different frames and aligned them all and then pulled in the meteors from each of the 5 shots to make a single shot with 5 meteors in it. And the next, please. The Zodiacal Light. This is early March sky looking east. There's that rotten cottage all illuminated on the horizon again, but nice view of the Zodiacal Light extending up and to the left. So next, please. So I've shown you 15 targets that I chose. There's another 7 that you can choose from. Moonrise or moonset at full moon. The moon or a planet next to a deep sky object. I'm not sure how you're going to get the moon next to a deep sky object without overexposing one or underexposing the other. An asterism, they particularly remark the Big Dipper or the Summer Triangle. I assume if you can find a large enough asterism, they would accept something else as well. Aurora, 2 or more images showing movement of a planet or an asteroid, Uranus or Neptune marked in a picture, and noctilucent clouds. So next slide. Basically, you take your pictures, you name each image according to the title of its requirement, scale the pictures to 1200 pixels on the long side, zip them all into a folder, add the completed application form, it's a PDF, and your documentation on how you took all the pictures, and email them all to the chair of the imaging certificate committee. So next slide. Depending on any feedback that Mick gets on this talk, I hope to be able to talk about the solar system and the deep sky certificates at the next 2 meetings. Any questions?
Yeah, Rick, we've got one in the Q&A.
Yes?
The
lens I used, it would vary. The very wide angle ones are mostly the 10 to 22 Canon lens. These are on a Canon 60DA cropped sensor. And then I think there's one of the shots, the Geminid meteors was actually taken with an 8mm Rokinon, no, Bauer fisheye lens.
Alrighty, and I had a question for you.
Okay.
Would Bob Olson's photos from back in the summertime when he was in Florida and included the alligator, would they count?
If they've got stars in them, yeah.
I'm sure with a bit of photoshopping, Bob could organize that.
Yeah. I think an alligator would constitute a horizon.
Yeah, or a new constellation. Who knows?
Yeah, yeah.
Anyway, thanks, Rick. And look,
sorry to interrupt, but I can't put a Q&A in there. But I just wanted to point to people that when I did my submission, several photographs were rejected because they had recognizable people in them. I like taking pictures at star parties, and they didn't want people showing recognizable faces.
Oh, that's something I was unaware of.
I think I was the first one to do that.
Right.
Okay, but nothing about alligators.
I think if you get a release, subject release from the alligator, you're okay.
It's okay. Andrea has asked, she says that the certificate says you must submit 15 from a following list, but can you do duplicated, i.e. 2 Milky Way or Eclipse?
Yeah, no, I think the desire is that you should sort of broaden your horizons, if you will, and include only one of each.
Okay, that's your understanding?
Yeah.
And when will you be back?
I.e. next month.
Yeah, okay,
next month, if the time's available.
And that'll be on Planetary?
Yes, solar system.
Solar system. Okay, so all you images out there, stand by for that one. So thanks, Rick.
Thank you.
And we're over to the observation reports. Now, before jumping into these, I have a request, and I put it out to the images mailing list that I maintain, but I'm going to say it out loud now. I'm wondering who amongst you would be willing to contribute to our fabulously provisioned website the raw samples of the raw images that underpin the types of stuff that now is about to be presented in these reports. And I'm asking that on behalf of idiots such as myself, who will never actually have the kit to go out and do the sort of deep sky image capturing that our colleagues do, but would still like to have the materials against which to build up skills in post-processing. So that's an open question, and I'm willing to take open or discreet answers at meeting chair at ottawarasc.ca. So with that, please, over to Taras.
Hello, good evening. This picture of Comet C 2017 K2 was taken on June 26 from Fred Lossing Observatory. Astronomers estimate that this comet has been traveling from the Oort cloud for some 3 million years in a hyperbolic orbit. It first became visible in small telescopes from the northern hemisphere in May and will remain visible until September. 3 days ago, 2 actually days ago, the comet was at its closest approach to Earth. I had a chance to take a few more shots of it on July 2nd and then July 8th, but still have to finish processing those pictures. The comet was much brighter, a little bit brighter rather than this, and you could see the tail more clearly, although it was not that prominent. Let's go to the next slide. And these are well-known objects, Lagoon and Triffid nebula from the center of Milky Way. This picture was taken with a modified DSLR camera and 135mm tele lens, also from the FLO site the same night. This is equivalent of 20 minutes exposure with f2 tele lens. I stopped it down to f2.8 and the Star Adventurer lightweight sky tracker. I like the amount of details that showed up in both nebulae and lanes of dust in our Milky Way. And these weeks are the best for observing these objects, as the center of Milky Way is visible throughout most of the night this season. Let's go to the next slide. Yeah, and this is the close-up of the Lagoon, also taken with the modified camera, but this time with my Schmidt-Cass telescope. I also used a dual narrowband L-enhanced filter to reveal a bit more details of hydrogen and oxygen. And the total exposure of this image was about 40 minutes. And let's go to the next slide. And later that night, or rather in the morning, I also imaged Jupiter, which was about only 25 degrees up in the sky. Not high enough for some details to show due to a bad seeing, but with the next few weeks, the planet's position has improved, and now it can be seen at around 30 degrees above the horizon while rising much earlier. Let's go to the next slide. So this is the close-up. If we take a closer look, it was about the same time, same location. If you look for this planet tonight or this weekend, it will be already about 40 degrees above the horizon, around like 4 o'clock in the morning, southeast direction, seeing as a very bright star. And let's go to the next slide. And again, from the same night, Saturn, early morning hours of June 26th. It's 30 degrees above the horizon around 3 a.m. or so. These days, it's seen a bit higher than that, but it will be at the opposition on August 14th. We're hoping for good seeing and clear skies to see more of this beautiful planet. Thank you.
Okay.
Well, thanks, Taras, and over to Richard.
So the lunar challenge this month was Mons Pico. And I was a bit late in the phase of the moon to catch it with its best combination of lighting and shadow. So this is a few days further on towards gibbous. Next slide, please. Here's the labels for it. And Mons Pico is a single isolated peak in line with the Montes Tenerife. And then there's a second isolated peak just a little bit down and to the right called Pico Beta. Both are in Mare Imbrium. Now, as I say, this is not exactly the best view of the light and shadow on those mountains, but I was very interested to see on the same picture, way up in the north, there were two really very prominent craters that I hadn't really paid much attention to before. In particular, Anaxagoras, which looks to me like it would be of the same youth and prominence as Tycho in the south. But normally it's hardly visible because it's way up on near the North Pole. But because of the current configuration of the moon, the libration, we're seeing the moon low in the southern horizon. And so we're seeing the northern side of the moon more than the southern parts. So it was quite prominent in this picture and also in the visual observation. Next one, please. And if you remember June 4th, that was a lovely night for the star party at Diefenbunker. So I was showing off my equipment for electronically assisted observing. And I thought it might be a fun idea to show the beginner challenge object, which is M107, a globular cluster. It was pretty easy to find in the south, following the line of the 3 stars at the front end of Scorpius, up into Ophiuchus, and then back again a little bit. So I was taking the live stacking view of these, but that builds up an image on my computer so that I can then process it afterwards. Next one, please. Now, the intermediate challenge was quite a challenge for my little telescope. But when I looked it up on Stellarium, I noticed that the field around this particular object, ARP 270, was a cluster of many, many, many small, tiny, faint galaxies. So I thought I would give it a try and see what I could get out of it. Next one, please. And on this labeled image, which I did using Stellarium, I did capture a lot of little faint red galaxies. Now, Stellarium was a little bit confused. When I asked it for ARP 272, it actually pointed me towards NGC 6054. But Wikipedia set me straight. No, that single galaxy is not the one they were talking about. ARP 272 refers to a pair of interacting galaxies, which is NGC 6050 and IC 1179. If you go back to the previous one, you can see, yes, there are two little faint galaxies there, so close that they might actually be interacting. Thank you. Okay, next one, please. Now, M106 was a challenge object from a couple of months back, but I just couldn't take a picture of it at that time because it was so far overhead. My particular equipment configuration meant that the camera was bumping right into the top end of my tripod. So a couple of months later now, I can actually get a good view of it. Not a terrifically long view of it because it sets behind my house rooftop in my backyard, but I did capture it, and it was quite an interesting galaxy because it has a lot of very distinct dust lanes cutting through it. So a very nice target. Next one, please. Well, it's goodbye galaxies, hello nebula for the summer. And here is my first try at one of the summer nebula, the North American Nebula, with the Pelican Nebula off to the lower right. This was on the Saturday night of June 18th and 19th, and I was very surprised to find that I was the only one there at FLO. But it was a lovely night. The bug repellent worked very well, and I got some nice long exposures. Unfortunately, I think I did bump into my tripod at some point because I couldn't take as long exposures as I thought I would be able to. I was drifting a little bit in declination, and my mount doesn't have a motor on the deck drive. But anyway, I got the nice set of 200-second exposures of this nebula. Now, an interesting thing about collaboration between RASC members here, I showed this picture to Andrea a couple of weeks ago, and she took a look at it and said, "Oh, your sensor's tilted." And I hadn't recognized that was a problem, but it turns out that yes, something in my imaging train is actually tilting the sensor with respect to the image plane. So I've ordered a new piece of equipment to try and fix that one, and we'll see if I can get a better picture next time. Thank you. That's all for me.
Thank you, Richard, and thank you, Andrea, for her advice. Over to you.
Thank you. Yeah, so I almost cried because tilt is a very tricky thing to get out of your imaging train. So this was a picture I took during the lunar eclipse in May, way back in May. So I had that night, I had 3 different cameras going, trying to do 3 different things. And I ran into Paul and Oscar, and they kept trying to talk to me, and I had 3 different cameras going. And so this was the image that I had worked the hardest to get. And as you can see, I had some clouds coming in the side. So the intent here was to try to capture the nebulosity around Rho Ophiuchi, which is around Antares, which is the red star that you see there. I wanted to try to stack the stars and then have the moon somehow blended in. And it probably would have worked, except I lost my coordinates at home and I was in the wrong part of the sky for a long period of time. But I managed to get maybe 5-6 minutes of exposure. I used an 85mm lens, so it was wide enough that I would get a little bit of Scorpius and a little bit of the moon. And then I did some short exposures of the moon, because the moon is even at totality, and this was at the totality phase, it's still quite bright. So it was the right idea, and it would have been fun had it worked out, but I still think it looked quite pretty because it's a wider view of the moon that you don't normally see. Next. And the second camera setup that I had was what I call the backup, the safe camera. Nothing goes wrong with this setup. It was using just my DSLR with a 400mm lens. And because I have a crop sensor camera, the effective focal length was almost 600mm. Now, the key to this photo, and I never knew this, but I figured it out at the last lunar eclipse last November, was when the moon is fully eclipsed, it's really dark. You cannot get a long enough exposure on a tripod during totality, or you're going to get a blurred moon. So, and I think it was Alan Dwyer that had a blog on this very issue. And at the last minute, I realized I needed a star tracker. So you need a star tracker for the deepest, darkest part of the eclipse. I actually, so I tracked the whole time, which is great because you don't have to think, the moon is just tracking. And then by the very end, when the moon was fully eclipsed, it was almost 10 seconds of exposure. And you can even see the little stars that are coming out around the full moon, which is fun because normally you don't see stars with the full moon unless they're photoshopped in. And those stars were not photoshopped in. And then I just stack them in Photoshop, the different exposures, and then you do a blending mode called lighten, and everything just lightens up and shines through, and it gives you this little collage. Next. And this, so everybody shoots the Whirlpool Galaxy, and everybody knows M51. And I didn't really mean to take a picture of it, but I was imaging another galaxy, and I was all set up for galaxies, meaning I had a very long focal length on my telescope. I was shooting at almost 2,000 millimeters. And it was the night of the June star party, which was a very nice, beautiful night. And my other galaxy had set. So I thought, well, what else am I going to do? I'm going to find, oh, the Milky, the Big Dipper was up ahead. So I took a test shot of M51, and I loved how it was very vertical in the picture. So I thought I would take a few images. So after a few hours, I had a black and white photo of M51. And I thought, oh, great. Now I have to go and do another night and get color information. And, you know, shooting at this imaging at this focal length is kind of tough and tricky, and everything goes wrong all the time. But then I realized, and this was kind of the neat thing, I already shot this galaxy last year in color with a totally different telescope and a totally different setup. But to combine color and a black and white photo, they don't have to match. PixInsight can register the two images, and it doesn't matter if your color is blurry because all the detail is in the black and white. So I merged the two photos, and boom, I had color. So that was the sort of neat thing that I learned with this image, was how to use old data and combine it with new data. Next. And so this, the next couple of images are pictures of the sun. And I had ordered this little tiny solar telescope because I thought I might use it for astronomy day in the spring, but it never arrived in time. And it's literally the smallest, tiniest telescope. It might weigh like 3 pounds. It's called the Lunt 40 millimeter H alpha scope. And I put it on my star tracker, and basically I look at the sun every single day. I'm incredibly obsessed with the sun. And unlike a lot of our deep space objects that we look at, the sun changes every day. Every day there's something happening. There's explosions, there's filaments and flares. And that's because currently we are going through a solar cycle of high activity. What's the next one? Yeah, this is a close-up, which I thought was kind of wild. It almost looks 3D. The white, this is an inverted image. And a lot of people who take pictures of the sun in H alpha invert the image. And so the very white spots that you see are actually sunspots that are dark, and that filament is a solar flare, and it's heading towards the edge where it will become a prominence, like you see the little black prominence. So yes, I mean, basically I spent the whole day imaging the sun today. I've given up on, I think I may give up on the night sky. I get to sleep this way, and I'm quite enjoying the sun and my little telescope. That's it.
Well, beauty. And I totally commend you on your aspirations for nighttime sleeping. Well done. So next, please.
Hello. This is one of Oscar's challenge objects. It's M107. We've seen it already. It's 21,000 light years away. And the most interesting thing about this thing for me was it was added to the Messier catalog by Helen Sawyer Hogg, a well-known Canadian female astronomer, in 1947, which is the year I was born. So it was clearly to celebrate my birth. Next image. Another challenge object. This is a galaxy pair. So which one is it? Where is it in this? Next image. Right there. And it's a galaxy pair, and you can't really tell from this image, but if you look in closely, next image, you can just barely see that it's actually two images. There's two galaxies there interacting. It's 251 million light years away. Next image. And another Oscar challenge, ARP 272. And again, all kinds of galaxies, which has been pointed out to us by Richard's images. And which one is it? Well, this is actually a galaxy trio. So next image. The two big ones are those two there. And if you go in closer, you'll see the trio. Next image. And you can see there are actually three interacting galaxies in the image. And that's 150 million light years away. Next image. Yeah, this is the Eastern Veil, or network image, the network nebula. And this is sort of the expanding edge of a supernova, which occurred 10 to 20,000 light years ago. And it's a star about 20 times the mass of the Earth blew up. It's 2,400 light years away, and it's visible in a telescope if you have an O3 filter on your telescope. It's actually quite spectacular and looks a little bit like this. You know how a lot of things you look at in your telescope kind of look like faint gray fuzzy things? Well, in a big telescope, this looks not unlike this, except not color. Next image. This is the other half of the shock wave going in the opposite direction. This is the Western Veil. It's also called the Witch's Broom. And I just absolutely love the look of it floating over top of the star, which happens to be 52 Cygni. Again, a very pretty image. Just a note here, the blue is ionized oxygen and the red is ionized hydrogen. Thank you very much.
Okay, Bob, thank you. Brian.
Okay, thank you. Hi, everybody. I've got my own little witch's broom right here. On July 6th, I went out in the backyard, just going out and having a look at the moon, naked eye at first, just before supper. The moon was just approaching first quarter. And so it was looking very nice up in the daytime sky. I'm a terrible photographer of anything in the sky, but I thought I'd do something with the leaves of the tree and that, but there are no recognizable faces in the tree. This got me thinking afterward when Mick threw the cat among the pigeons, and he started asking this question about what constitutes basically a legitimate observation. We talked about what equipment you might be using, and you know, as technology progresses, then people start using that, and what can we do with that new technology to peel away more and more layers of the onion, as we're seeing with the James Webb images that have come to light. So that's all very interesting. And if we go to the next slide as well, please, Chris, thank you. Yeah, so just some nice images, and for me, I like to just have some calm time with the moon, just as another celestial object, as a companion to the Earth. Now, since we're talking about observations in the spirit of full disclosure, this was a series of stacked images created by blinking my eyes for a bit. in amazement at looking at the moon. And then I snapped the shutter on my Canon Rebel T6. I was on a telephoto lens there, but it was nice with a bit of cloud there. And what I'm waiting for right now is around, I think 10:45 is when we'll have moonrise, and Saturn will be quite close to the moon. So I'm going to keep an eye out for that as well. But it's just a nice, calm observation to make, and it was very enjoyable. Thank you very much.
Well, Brian, thank you for your introduction of neocortical stacking techniques, and we'll see you next month. Who's up next?
That'd be me.
Hello, Paul. Take it away.
Thank you, Mick. I'll leave my video off because I'm getting notification that my connection is soft as usual out here out in the hinterland. So you'll have to bear with me on that. Hopefully the audio won't cut off. But anyway, good evening, everyone. And well, I finally had a few opportunities to test out the ZWO ASI 294 MC Pro camera on the rich fields of the Milky Way. And this is one of the views I got with it. This is the area centered on the North American nebula, NGC 7000. And I took this only using a 50 millimeter f1.4 Canon lens on the camera to get a wider view than through one of my telescopes. The camera was mounted on an Ioptron sky tracker to keep the view centered. And this image is a stack of 30 10-second exposures. I continue to be impressed with the sensitivity of this camera and its ability to record even faint detail in relatively short exposures. In conjunction with a fast lens, you can go pretty deep fairly quickly. Next slide, please. So continuing in this vein, I first wanted to show, especially for relative newcomers in the world of astronomy here, I first wanted to show you this image taken by Adam Bloch of Edge-on Galaxy NGC 4565 to put things in context. This barred spiral galaxy is believed to be similar in structure to our own Milky Way. And for someone living there, they would see our Milky Way galaxy in much the same way as we see theirs. Next one, please. So the next image I'll show you is a region of our galaxy comparable to this portion of NGC 4565. But taken obviously from within our own galaxy. You can see on this image that the region borders on the central bulge of the galaxy and goes along the adjacent spiral disk with its very obvious dust lanes. So next one, please. So here's the comparable view from our own galaxy. This was also taken with the ASI 294 MC on the Ioptron sky tracker, but this time using a Bauer 16 millimeter f2 lens to capture a much wider region. It's a stack of 30-second exposures. You can see the view here is littered with stars closer to the center of the galaxy than our location, about 2/3 of the way removed from the core. And the bright central bulge of the galaxy's heart is very prominent. Just as in NGC 4565, our galaxy is rich in thick dust lanes that obscure the view of the galactic center. Dotted among those dust lanes are some of the beautiful red nebulae that are favorite targets for many of us at this time of the year, including M8, the Lagoon Nebula, and nearby M20, the Triffid. They're both just to the left of the image's center. M17, the Swan, and M16, the Eagle, are just to the left of center. Next one, please. So my final image tonight is of a comet that just recently caught my attention. That's Comet Pan-STARRS C 2017 K2 that Tara showed you an image of in his collection. So a bit of background here. This comet came to us from deep within the Oort cloud, where it's been floating around since the formation of our solar system about 4.5 billion years ago. So roughly 3 million years ago, while our distant ancestors were still swinging from the trees, this object had a near encounter, or perhaps even a collision, with another body out there, and so began a journey in towards the sun. It's taken 3 million years, but it has finally reached within the planetary orbits of our solar system. This is an interesting comet that was just discovered in 2017, while it was still out between the orbits of Saturn and Uranus. And at that time, it was the most distant active inbound comet ever found. It was studied subsequently with a Hubble Space Telescope, and it appears to have a nucleus of about 18 kilometers in diameter, so not a bad size, kind of similar in size to Halley's Comet. I imaged the comet 12 days ago as, excuse me, as part of, oops, I'm sorry here, I lost my page here. I imaged the comet 12 days ago as another test of the ASI 294 MC Pro. Next one, please, Chris. There we go. I think it's running there. It might be a bit choppy on my video, but so instead of stacking numerous images of the comet to create one final view, I decided to stitch 134 consecutive images together to form this time-lapse sequence. This was taken with my 11-inch Edge HD and shows the comet's motion over the course of 1 hour and 45 minutes. The comet was only about magnitude +8, so not particularly bright, and definitely not visible to the naked eye. Still, a backyard telescope will allow you to see it, and it just made its closest approach to Earth yesterday, in fact. It's up in Ophiuchus, currently very near Messier 10, and in a few days the moon will rise later in the evening, giving us a darker sky view of it. So hopefully we'll get some clear skies, and if you're interested in checking it out, it should be visible in even a relatively small telescope if you've got a reasonably dark sky. That's it for me this month. Wishing you all clear skies, and we'll chat again soon. Take care.
Okay, thank you very much, Paul, and that's a lovely time lapse. Oscar.
I'm not seeing Oscar as a panelist right now. He's apparently not joined us.
Okay, I don't know how to speak to these. Chris, you wouldn't have any notes?
No, I don't have notes handy.
Okay, I think we can just roll them through, or maybe
I think Paul may be able to speak
present
to this
them
one
again next month.
Okay.
I can give you a bit of insight on this one. As Andrea mentioned, we met Andrea, Oscar, and I incidentally at the same site. That was quite by accident. So this is over the Lower Rideau Lake, and we did have clouds roll through after totality. So we did get a good view of totality. But as the clouds rolled in, Oscar decided to do something a little bit different. He launched a drone of his, and from the drone camera decided to image the eclipse. So rather kind of a cool thing to do. And this is, I think that this is the unprocessed image of that the drone captured from several hundred feet in the air of the total lunar eclipse over the Lower Rideau Lake.
Well, I think that's an absolute first for RASC Ottawa, is it not?
It may well be.
I mean, last month we had his photos of the drone. Now we get the photos from the drone. Good stuff.
Yeah,
everyone else struggles to have a sturdy camera on a tripod that won't move, and here he goes and blows away that theory as a moving camera.
I love the way that worked out because, yes, as you mentioned last month, I think it's in Astronauts as well. There, I actually once the clouds came through there, and I saw Oscar's drone fly overhead. And he said to me, "Is that a problem?" I said, "No, not at all." And so I actually imaged the light trail of the flashing lights of the drone as it passed overhead. And while I was imaging it, it was imaging this view. So
that's exactly what I was thinking of, Paul. Thank you. All righty, next one, Chris. Okay, so Oscar is absent. We will now move to his observing challenges. As you've heard people whine and complain, last month it was Messier 107, 272, whether that was 2 or 3, interacting galaxies, NGC 6692, and Mons Pico on the moon for the lunar challenge. So this month, what do we have? Chris. So, beginners challenge M80, globular cluster shown up on Andrea's earlier lunar eclipse photo, 7.3 magnitude, 10 minutes in diameter. Next, please. Intermediate challenge NGC 6207, a spiral galaxy in Hercules, 11.7 magnitude, so quite a bit deeper and about a third of the size of the previous target. Next one. Advanced challenge, Terzan 7. I have to say, I have never heard of the Terzan collection before. It's apparently a globular cluster in Sagittarius, 7.3 minutes apparent size and 12th magnitude in brightness. Then for our lunar challenge, we have Plato. Well-known lava-filled impact crater, over 100 kilometers wide and 1.5 kilometers deep. A good, well-known challenge object. So next one, Chris. To recap, M80, intermediate challenge NGC 6207, advanced Terzan 7, and for the lunar challenge, crater Plato. Now to the announcements, I believe. If you will, Chris. So the star parties have returned. We're up to our third one now, scheduled for Friday, August 19 at the usual location at the Public Library / Diefenbunker car park. There is a backup date if Andrea's online. Can you mention that rain date?
I believe it's the next date, the Saturday.
On Saturday, the 20th. Okay. Okay, thank you. So yes, get out there, join the fun. Next, please. Fred Lossing Observatory back in action. Notice the nice new photos and the new sign. And as most of you are well aware, this is a members-only facility. Guests are welcome in the company of members, and you're certainly welcome to bring your own equipment, as well as arrange for use of the telescopes on site, and contact Rick Scholes for more information about that on the website. Next, please. The observing star party dates at Fred Lossing. Next one coming up 2 weeks away, July 30th. And fingers crossed, waxing crescent moon will put on a nice show and not get in the way. Next, please. Usual club information. You can read for yourselves. I don't need to go over that. Next one, Chris. Okay, we got 59 tonight. Not bad for holiday season. Usual big thanks to everyone, particularly our out-of-town guest speaker, so to speak, Jesse Rogerson, all our presenters, our observation reporters. Thanks to our host, the RASC National Office, and the Zoom account that they allow us to use. Comments, ideas, propositions, complaints to meeting chair at ottawa.rasc.ca. Lagging. Okay, as stated at the outset, videos of tonight's meeting, including the presentations, observations, challenges, are available on our fabulously well-positioned website, as is the monthly newsletter Astronauts, all at ottawa.rasc.ca. And finally, to close out, next meeting, provided that Rogers don't get up to any sillinesses, Friday, August the 5th, usual bat time, usual bat channel. So thank you all for your attendance, and looking forward to seeing and hearing from you then. Thank you.